folks, welcome to the Late Night Math Show. Now today's episode, we will be speaking with my friend Plato. Hey Plato, nice of you to join us today.
Of course.
So to start off, tell us a little bit about yourself.
Well, I'm a Greek philosopher. I was born in 428 BC in Athens, or 427, I'm not really sure, I always forget. My aristocratic parents, A and P, have my two brothers and I also have a half-brother. Some of my notable works, as you may know of, are Apology, Statesman, Laws, Charmides, Philebus, Timus, and Sophists, just to name a few. I'm also the founder of the Academy in Athens, which was the first institution of higher education in the Western world. You know, no big deal.
That's very nice. Speaking of great communication, I would like to ask you about one of your notable works, Timaeus.
Oh yes, it is a dialogue, or more so a long monologue, in which is given by a character, Timaeus of Locri.
Very interesting. The media has been buzzing about one particular subject, or should I say 5 subjects, that Timaeus spoke about, the Platonic Solids.
Very true. The Platonic Solids were discovered by early Pythagoreans, perhaps in 450 BC. There is rumor that the Egyptians knew about at least 3 of the 5 solids. Their work actually influenced the Pythagoreans themselves.
Amazing. Can you tell us a little bit more about these solids?
Yeah, of course. So there's 5 solids: the tetrahedron, the cube, the octahedron, the icosahedron, and the dodecahedron. Each solid is identified with elements that make up all of the matter in the universe.
And these elements are?
Fire, earth, air, water, and the cosmos. Fire atoms are paired with the tetrahedron, earth atoms with the cube, air atoms with the octahedron, water atoms with the icosahedron, and the cosmos with the dodecahedron.
Very nice. So what is Platonic Solids?
A Platonic solid is a 3D shape where each face is the same regular polygon. The same number of polygons meet at each vertex or corner.
Can you give me an example?
So the cube is a Platonic solid. Each face is the same size square, and 3 squares meet up at each corner.
Can you tell us more about these 5 solids?
Yes, of course. So, the tetrahedron, which is this shape right here, has 3 triangles that meet at each vertex, has 4 faces, 4 vertices, and 6 edges. And then we have the cube, which has 3 squares that meet at each vertex, 6 faces, 8 vertices, and 12 edges. And then we have the octahedron that has 4 triangles that meet at each vertex, 8 faces, 6 vertices, and 12 edges. And then we have the dodecahedron, which is 3 pentagons that meet at each vertex, 12 faces, 20 vertices, and 30 edges. And then our last one is a icosahedron that has 5 triangles that meet at each 12 vertices and 30 edges. We're not very good at putting shapes together,
But
so here's the layout.
why are there only 5 solids?
The simplest reason, of course, is at each vertex at least 3 faces meet, maybe more. And then when we add them up, the internal edges that meet at the vertex, it must equal less than 360 degrees. We also know that a Platonic solid's faces are all identical regular polygons. So a regular triangle has internal angles of 60 degrees. So we can have 3 triangles that will equal 180, 4 triangles that will equal 240, or 5 triangles that will equal 300 degrees. And then a square has internal angles of 90 degrees, so there's only 3 squares, which will equal 270 degrees. As for a regular pentagon, they have internal angles of 108 degrees, so there's only 3 pentagons that will equal 324 degrees. A regular hexagon, though, has internal angles of 120, so it equals 360 degrees, which won't work because at 360, the shapes flatten out. So a regular pentagon is as far as we can go. Anything else that has 360 degrees or more at a vertex is impossible.
Is there another way to test if a solid can be a Platonic solid?
Yeah, of course, I call this the Euler's formula. It says, for any convex polyhedron, which includes the Platonic solids, the number of faces plus the number of vertices minus the number of edges always equals 2. It is written as F plus V minus E equals 2.
Can you try it out on one of the shapes?
Let's try it out on this cube right here. The cube has 3 faces, 8 vertices, and 12 edges. So the equation would be 6 plus 8 minus 12, which would always equal 2. To see why Euler's formula works, imagine taking the cube and adding an edge, say from corner to corner of one of the faces. When we get an extra edge plus an extra face, 7 plus 8 minus 13 would equal 2. Likewise, when we add another vertex, say halfway along the line, we get an extra edge too, which would equal 6 plus 9 minus 13 is 2. So no matter what we do, we're always going to end up with 2.
Wow. Thank you so much for the information, Plato. Thank you for having us at the late night show, the late night math show, and I will look forward to seeing you again.
Thank you for having me.